The reason the time constant is such a big deal in electrical circuits with capacitors is that it enables us to control how fast something happens in a circuit. In other words, for the first time we are able to have a say on the timing of events within circuits. And this is really important right across the board in virtually every electrical thing that you use in your lives. The time constant is often called T, capital T, or more correctly tau, which is the Greek version of. You'll see both as you float around on the internet. And interestingly and surprisingly, it turns out that if you multiply ohms by farads, you actually get seconds. When a capacitor is charged up to the value of the cell and then discharged through a resistor, the maximum current that you get in that discharge process is simply V0 over the value of the resistance. Now, remembering that as a capacitor dissipates, loses charge, the PD or voltage on the capacitor drops. That means the current is going to reduce, and the speed at which it reduces is going to depend on the size of that resistor. Why? Because that resistor limits the current in the circuit. Therefore, if you increase the size of the resistor, that means that the maximum current drops, meaning that the time for it to discharge takes longer. The discharging formula for the current in a capacitor is given by I equals I0 e to the minus t over RC. This formula can be used to give us the amount of current that will flow in the circuit at any time, assuming we know the values of RC, the time constant, and also the initial current. What happens if we set the value of time equal to RC? In other words, they both have the same value in seconds. This leaves us with e to the minus 1 is going to be equal to I over I0. E to the minus 1 is actually 0.37, and so this means that the ratio of the existing current now divided by the maximum current at the start is 0.37. 0.37 is of course 37%, and so the time constant is the time taken for the initial current to fall to 37% of its initial value. As you could probably see, the value of current is never going to get to zero. But in electronic circuits, we like to do an awful lot of hand waving. Who cares if the current is a microamp? It's basically zero. Suppose we wanted to draw a graph of time along the x-axis and current up the y-axis, and we split the x-axis into RC intervals, 1 RC, 2 RC. Remember, RC is just a number, 5 seconds, for example. We know that in each of those RC intervals, it's going to fall to 37% of its previous value. And it turns out that in the wonderful world of electronics, we say that when you get to around about 4 RC or 5 RC, the capacitor is basically fully discharged. Now, you know that of course it isn't, but the amount of charge or voltage that is left and the current it can provide by this point, by 5 RC, is as near to zero as makes no odds. And this is the point at which the time constant introduces our ability to control time. By setting the values of R and C carefully, we can now choose how long, say, a voltage takes to fall to 37% of its initial value. And then we can use that drop in voltage to trigger something else. For example, a motor turning on, or a whole host of other things. And simply by varying the value of the resistor in a circuit, we can say how long it's going to be till our event is triggered. It's triggered if we trigger it at, say, 37% of its initial value. So here we have a way to control time, and this, as you can imagine, is really useful.